So thank you very much for inviting me to present this paper. This is co-authored with Harjoat Bhamra and Raman Uppal. We're interested in belief formation in financial markets, which is a question that has received a lot of attention recently, but has traditionally maybe not received so much attention in asset pricing. So the classical view has sort of been a representative agent model where there's gone a lot of work into thinking about the pricing kernel and what needs to be done to fix asset pricing, given a lot of puzzles that show up. But the rational expectations paradigm, which is a wonderful paradigm, but it's been sort of ruling in suggesting that there's not all that much that we need to do with respect to thinking about beliefs in this setting. And there's been a lot of evidence recently that indeed beliefs are much richer than what will be shown in such a representative agent rational expectation setting. So a lot of behavioral effects have been noticed, where it is pretty clear that at the individual agent level, beliefs vary a lot among agents, and in a fairly systematic way, for example, suggested by the local bias literature. So what we're going to do is we're going to introduce a framework, a flexible and general framework, which is based on the psychology literature on the concept of psychological distance. We will apply this to a data set on investor level portfolio holdings in the Finnish stock market, and show that the predictions of this framework it sort of fits nicely and seems to explain a lot in this market. So I'm just going to flag at the onset that what we're not going to do is to prove or separate this framework from some other explanations. Especially there are some information-based explanations on the information channels that it's sort of the data set we have. It's not well enough identified for us to be able to do a strict identification here. So this will be, the empirical evidence will be suggestive, but this is not really the goal of the paper, which is more about the framework and showing an example how applicable it is. So our starting point, as I said, is the social psychology literature. There we have the construal level theory, which basically takes as a starting point that the only thing we can really experience is what is happening right now, right here. And anything else, any decision we make about something that is sort of further out in time, or what dividends am I going to get from a stock, or am I going to buy a stock in a company that is situated geographically in another part of the country. Really, we need sort of some frameworks to even make decisions about this based on our experiences here and now. And that's what construal level theory does, is to set up this, introduce a framework for understanding how we can make decisions about such distal objects given what we know about the here and the now. So it starts with a reference point, and that is where I am right now and my experience right now. And then what I do with respect to deciding about objects that are further away in some abstract space. This is sort of very general. We'll mainly think of this in the data as geographical distance. But this could be, there's a long list of different different dimensions that affect psychological distance. So, for example, cultural distance. We're going to apply this directly to investments. Our goal is to build upon this idea and come up with a model for how do investors behave when choosing a stock portfolio. But a cultural distance here could, for example, be whether the CEO of the company speaks the same language or comes from the same culture as I do, which, if not, might increase the psychological distance and therefore it might affect my behavior when investing in such a stock. So, everything is going to be abstract. We're going to have some metric space for us, but I want to sort of flag for that the framework is very general and flexible, and we think that it can be applied to many different situations. Okay, so the way we think about this is, and we're building on the universal law of generalization introduced by Shepard in how do we set this up mathematically. Basically, we have an investor who is situated at the reference point, X here, and is thinking about investing in among a universe of stocks. Now, the investor understands very well what is going on and happening in the immediate neighborhood, and maybe he or she works at a firm, a publicly traded firm, that is completely understood and sort of has full experience with and can estimate expected returns, volatility, understand the cash flow statements of this company. So full information in line with the rational expectation framework about this firm that is in the immediate neighborhood. And now the investor is going to draw inferences about this with respect to how to behave when thinking about investing in other companies that are in this abstract psychological distance space, not as close. So mathematically, we assume that there's a general metric space that measures distance d between different objects, in this case firms. When deciding whether to invest in a firm that is not right by the investor, she decides to draw inferences based on the experience of the firm that lies right where she lives. The way this is set up in line with the universal law of generalization is that so Shepard assumes that there's basically an equivalence class of objects that are similar. So that means that if you belong to the same equivalence class, then you can draw inferences about another object from the object that you have experience with. So there's some ball in this geometric space with some radius, and if you lie within this radius, then you belong to the same class of objects, and you can draw inferences about this other object that is a psychological distance. But the issue is that the agent does not know the center of this ball nor the size of the radius. So it's basically an inference problem. What are the chances that this distal object belongs to the same equivalence class as the object that I have a lot of experience with, the firm in my immediate neighborhood? Using the principle of maximum entropy, Shepard shows that this is actually a well-formed problem where one can then derive some sort of nice tight specification for what the chance is using Bayesian updating of the distal object being in the same equivalence class as the closed object. So the only assumptions we make here is that there is some maximum size of this region, basically of the radius of this ball, basically meaning that there are some things that are so far away, so you just don't trust that you can draw any inferences about those distal objects. Otherwise, we basically make no further assumptions. So, I think this is based, so I'm not an expert on the psychology literature, but clearly this whole theory is based on some very intuitive observations in how we behave and how we draw inferences about the unknown from our own experience, which of course genetically has been sort of very helpful for us over time when understanding whether we should eat certain fruits that, you know, looks a little bit like, but not quite like a fruit that we have experience with, and is it poisonous or not. My own experience, I have an example, you know, if I travel to some region where I don't really know, I don't have a lot of experience at all, and I sort of am to decide whether I should get into a cab or not. You know, clearly there are a lot of cues that I take with respect to whether I can draw inferences about my cab experience from where I am in this place that I'm not used to. You know, how much does it look like a cab I'm used to? Do they have a meter? You know, am I really comfortable with getting into this cab, or will they overcharge me or take me to the wrong place or something like that? So I think we're sort of doing these type of things all the time, and I think it's fairly natural to think about this in a stock investment perspective too. So what we derive then is a mapping, which is sort of really nice because it's intuitive and it's based on only two parameters. So a mapping between the psychological distance and the probability the investor puts on being able to draw inferences about the distal object based on the experience of the object in the neighborhood. So this phi HN here, H will stand for households and N will stand for the end stock, will then be a function, an exponential decreasing function with some slope of the psychological distance. And again, think of spatial distance if we want to interpret this as local bias, with some cutoff beyond which you're not going to feel that you can draw any inferences whatsoever. And that will then affect how the agent behaves when forming the investment portfolio. And it'll explain decreased portfolio holdings for objects that are further away. And also because of the cutoff will lead to a lot of other stylized facts that we sort of see in how investors behave. Severe under-diversification, correlation of portfolio holdings of agents that live nearby each other, etc. So we think of a strength there is that it's a general framework, and it leads to a nice tight specification that one could actually test in the data. We're going to look at portfolio holdings when we look at this relationship. And as I mentioned, you know, our goal is basically going to see if this specification fits nicely on a data set where we have portfolio holdings of agents at a very disaggregated level. Now, since we only observe portfolio holdings, there are limitations on how far we can take this analysis. So if one really wanted to tease out is this beliefs, you know, some type of survey-based data where we actually ask, so we know what the beliefs are of different agents would be needed, we think. Okay. So, nicely also, there are different example, different special cases nested here. If kappa is equal to 0 and this threshold d bar is equal to infinity, then we're back into the rational expectation setting. And we can avoid under diversification if we set d to infinity, but we have a kappa. The higher the kappa is, the more you're going to decrease your portfolio holdings quickly if the firms are not in your immediate neighborhood. Okay, so we put this into a fairly standard production economy environment. We have different variations, partial equilibrium, general equilibrium, and it basically all leads to very, very similar specifications. The investor takes the different distance that then maps over to what we call the trust function, which is the probability of being able to draw inferences about this other firm. And when we set this into a decision framework, we have sort of a macro foundation for this. One can also think about it as a robust optimal control problem, a la Hansen and Sargent. What falls out of this is that the agent basically forms a household or agent-specific belief that deviates from the true rational expectations beliefs. That is going to be a function of this this psychological distance function, where the agent says basically if the object is very far away, then the agent will revise down the probabilistic estimate towards the risk-free rates. So basically thinking about risk-neutral probabilities versus the true probabilities, this psychological distance function provides a mapping where the agent will lie somewhere between the P and the Q and get closer and closer to the Q probabilities the further away the object is. Yeah, thank you. This is all fairly standard stuff. I'll go through this very quickly. So Hansen Sargent robust control max mean. It leads to beliefs then that will be a weighted average then with this this exponential decay function. So so your beliefs and then also your portfolio holdings, those are the omegas here, will be the weighted average where the weight on the P is this this trust parameter here. If it is 0, then you're not going to have any trust, and therefore you're not going to invest in this stock at all, leading to under diversification. The data we have then to look at this is all the household holdings, the retail holdings on the Helsinki Stock Exchange, we don't have exact data for where we have at the postal code level data where these households are situated. So we're going to have to treat this at the postal code level. We lump all the households within the same postal code into one representative household and assume that they're placed in the at the center of that postal code. We're going to use spatial distance here as a proxy for psychological distance. But again, you know, one could throw in other variables here. One could have a higher dimensional distance function having multiple psychological distance factors at the same time. We have 125 stocks at this point in time on the Helsinki Stock Exchange. And the one thing we find, so, you know, immediately if one looks at severely under-diversified household portfolios, the median number of stocks they hold is 2, and the average number is like 5 or something like that. So, you know, very few stocks, and they don't rebalance often. So there's very little. We have a few years of data, but there's actually very little going on in the time series, which sort of suggests that there's not a lot of learning and updating going on with respect to this model. This is more like a model of priors, and they actually stick with those priors, at least if we look at their portfolio holdings. So it's sort of like you're stubbornly deciding that, oh, I'm going to stay away from these firms. So there are a lot of new models that have a more of a learning approach, but we think this, well, I mean, that is interesting, important too, but the priors here are actually a first order effect too, and that's what we're focusing on. Okay, so so what do we get then? So we focus on one date since there's so little variation over time. We'll just take a specific date, look at the cross section now of portfolio holdings of these different households. So we get a panel where we have stocks versus households, and we now see how this function, predicted portfolio holdings, given that we're looking at spatial difference, will fit the actual portfolio holdings we get. So we show that in log coordinates, we get a nice specification here where we can see what kappa, this decay parameter, falls out of the model. So we have various different tests here where you throw in a bunch of different fixed effects, firm, zip code, and some other information we have about the stocks. These sensitivity coefficients all come out highly significant. So that's the decay parameter. Here we've normalized Finland. So the size of Finland is 1. So this 3.18 means that you're going to decrease your portfolio holding by e to the power of minus 3.18 if you are thinking about investing in a firm far away in Finland. So a significant amount. The cutoff is estimated to be 0.17. So if you're more than 17% away from the size of Finland, you're basically not going to invest in those stocks at all. And since Finland is a very, you know, at least back in those days, it had a very large rural part. and most of the stocks where the firms are centered, we use the headquarters as a proxy for their position. They lie close to Helsinki. That means that there are a lot of parts of Finland where our model basically predicts that investors are going to hold very few, if any, stocks. Now, I'm also going to show very quickly that this leads to significant welfare effects, if we believe in the model, because the effects of under diversification are huge with respect to taking on too much risk, which is what we've seen. The House of Finance literature has shown us is something we see in the data. So that's the kappa estimate. Another, we do a bunch of tests in the paper. Another test we look at is this various versions of looking for under diversification, which basically is equivalent to saying that this D bar is less than infinity. And as I said, the estimate is that it's 0.17. So you're not investing in stocks that are more than 17% away from you in terms of the size of Finland. Now, one way of seeing effects of this under diversification and prediction of the model is that investors who live nearby, remember now they invest in very few stocks. But if you look at the stocks they invest in, it tends to be highly overrepresented investing in the same stocks, because those are the ones, all investors that live close invest in the stocks that are nearby. So if we look at the ratio between overlap between any two random investors that live in the same zip code of the random, if given that they invest in two stocks out of these 125, how many overlaps would be safe to see on average? Well, there's a high overrepresentation in the stocks they invest in. So this type of herding towards the same stock is also a prediction of our model. So we do a bunch of other tests there. I want to mention the last couple of minutes just the welfare implications here. These can be measured, for example, in the Sharpe ratios of the predicted portfolios contra what is the optimal portfolio. And this belief revision, so because of uncertainty or this non-trust, the households always revise their beliefs about the stocks far away downwards. So they think that they're worse than they are. They're more like the Q probability than the P probability. This is one thing where one could potentially test this against information stories, which typically predict that you're going to have noisy estimates of expected returns, but they're going to be unbiased. But here, everything is always biased down because of this non-trust that investors have. But this also means that they invest in portfolios that have much, much lower Sharpe ratio than what is optimal. So during the time period, the market Sharpe ratio was 0.59 in the Finnish stock exchange. And if we look at someone who lives very close to where all the firms are situated, still, the realized Sharpe ratio, according to the model, would be a lot lower than the optimal Sharpe ratio. And those who live far out in the rural areas have almost zero Sharpe ratios in the one or two stocks that they invest in because they're not diversifying. So real welfare costs of this, and this is sort of where you get your 0.34. This is where you get your 0.09. And if you're outside of this region, then you're down to 0.02 in Sharpe ratio rather than the 0.59. Anyway, what we think is a constructive, flexible framework to think about belief formation and behavioral biases based in the psychology literature, and leading to a nice tight specification that we think one could take even further with different data sets. Thank you.